Hello and welcome to this presentation today. My name is Sven Mika and I will be talking today about deep learning and neural networks. The title of the talk is From Perceptrons to Differentiable Neurocomputers, and I wanted to express with that this evolution that neural networks underwent through the last couple of decades. So this is also what we're going to do today. We're going to start with the perceptron. We're going to cover all the math that's behind the perceptron, and then we're going to slowly complicate things through the multi-input and multi-output, multi-layer perceptrons towards the newer architectures leading to something like the differentiable neurocomputer, which was published in 2016. But we'll also talk about many other architectures and topologies, such as LSTMs and convolutional neural networks. And we'll also look at the algorithms that we use to train these things. Meaning, we're going to look at gradient descent, what that is, and we're going to talk about backpropagation, which is, by the way, not the same as gradient descent. Sometimes they're used interchangeably, but they're not the same thing. Basically, they're used together. They kind of help each other out, and we'll look at that in all details, and we'll figure out how backpropagation works exactly. It's actually not that complicated as it is sometimes explained, but I think, or I hope, I found a way to cover this topic in an easier and understandable way, in a comprehensible way. So let's start. We'll start with the perceptron. The perceptron was invented or was developed in the 1950s by a guy called Frank Rosenblatt. He was a psychologist, and he was trying to find a simple model, a mathematical model, to describe the behavior of animal nerve cells. So this is an animal nerve cell here. It works just really quickly. It works like this. You have these dendrites here, and there are ion channels sitting in the membrane where these dendrites are. And if some signal comes in from the outside, from some previous cell or other cell, these ion channels, the signal comes in the form of a neurotransmitter, and then these transmitter molecules, they trigger the ion channels to open up, and then ions flow into the cell. So the charge changes, or the voltage changes, the potential changes between the outside of the cell and the inside of the cell. And if this potential, if this influx of ions reaches a certain level, reaches a certain threshold, the cell will fire a single signal down its axon. This thing is called an axon. And at the end of the axon, when this signal arrives here, there are other cells waiting here to pick up that signal again. And then the whole process starts again with the next cell. So there's this neurotransmitter being released that triggers channels to open up here, influx of ions, and then once some threshold is reached, a single shot through the axon. So he came up with this model here, which is really quite a simplification, of course. And a lot of biologists today, they criticize the neural networks, the fact that some of the neural networks researchers always say that we're trying to simulate or rebuild the brain with neural networks, which of course is not true. We're not trying to do that. We're just trying to build good and working models for passing on information from one computational node to another. Yeah, so this is all we do, and this is, I think, what he did, what Rosenblatt had in mind as well. And in my opinion, he was really successful with that. And it all started with this simple model, which is called a perceptron. The perceptron works as follows. You have different input features, right, which simulate or which represent these different channels here in the dendrite. So information can flow in here, right? You have, in this case, we have three input features, x1, x2, and xn. Those are numbers. Those are scalar numbers that come in here. Yeah, so you basically can represent them as a vector, as an input vector, with a different number of slots. And each of these inputs here gets multiplied with their respective weight. So this guy gets multiplied with this guy, and this guy gets multiplied with that guy. Yeah. So we have weight multiplications. The weights here are our machine learning parameters that we will later be able to tune and train and change depending on our data. And we'll get to that later, how that works. Right now we're just doing a multiplication. We're multiplying x1 by w1 and x2 by w2 and xn by wn. And then we're summing up all these, I forgot to say, sorry, I forgot to mention this special weight here, which is sometimes called a bias. And it always gets multiplied with 1. Yeah, so this one is not really an input feature, it's always 1. We multiply with this weight, and often in the literature you will find this weight is called a bias, or B. I here in this presentation folded it into this to this matrix set of set of weights here, because it makes the equations later easier. Then you don't have this bias term lurking around all the time. So when we're done with these multiplications here, we sum it all up. So basically there's this function here, sum function, summation function, and it looks like this. Yeah, so this is just what I just said. W0 times 1, x1 gets multiplied with w1, and so on and so forth. By the way, these weights here, they don't have to add up to 1. It's not a probability distribution. They can be negative, or they can have large values or small values, or be 0. It doesn't really matter. And what this is here, if you recognize this from your linear algebra class, is it's just the dot product between the input vector x, which is the vector of all these input features here, and the weight vector w, which is the vector of these guys here. Yeah, so this is the inner product, and the result of this is just a number, right, which is the sum of this here. Next, what the perceptron does, the last step, is it activates. But it only activates if the sum here that comes out of this block is larger than 0. Then the activation function will output a 1, and if it's smaller or equal to 0, it will output a 0. Yeah, so the activation function is a function of this summation block, and only activates if this summation yields a result that's larger than 0. And then the output is can only ever be 1 and 0. Yeah, with this type of activation function. This function, by the way, is called a step function because it's always 0, but it makes that step if the sum is larger than 0. All right, so let's try one example. We're going to now manually try to find some weights here to solve a certain problem. I'm going to simplify our model a little bit. We're taking away all these other weights here. We only have now 2 input nodes, x1 and x2. And we have 3 weights, the bias weight, we have w1 and w2. And again, I updated this equation here. I took away this n term, made it a little simpler. This is still the same. The activation function stays the same. And the problem we want to solve now is the AND operation. And it goes as follows. The inputs to our network can only ever be 0 or 1. Yeah, so basically we only have 4 possible input vectors: 0, 0, 1, 0, 0, 1, and 1, 1. And the output of the network, or the desired output of the network, is always 0, except for the case where both x1 and x2 are 1. Then the perceptron should fire. Okay, it should give us a 1. Here I wrote again that the inputs can only be 0 or 1. And so this, of course, this operation is called the AND operation because it only fires when x1 and x2 are 1. And now I want you to maybe pause the video and quickly think about which values for w you need in order to make this happen here, in order to make this perceptron behave this way. Just to let you know, of course, there is an infinite number of solutions because you can pick any real valued numbers for your weights. Alright, so maybe you tried it, or if not, I'll help you out now. What we can do is we can set W1 and W2 to both be 1. Yeah? And what that will do is if both x1 and x2 are both 1, we get a sum of 2, right, which is larger than 0, so we're happy it will fire. But now we have to check what happens if only x1 is 1 and x2 is 0. In that case, we'll multiply with 1, which is 1. This will give us 0. And then we have a problem, we're still larger than 0, so we have to set W0, or the bias, to something negative. Yeah? And the solution is, or one possible solution is, to do it this way here. Any number that's smaller than -1 is fine. Even -1 is fine, because it will if x1 is 1 or x2 is 1, it will push the sum back to 0, and then it will not fire. Yeah. So here's one solution. W1 is 1, W2 is 1, and W0 is -1.5. Okay, because this was so much fun, we're going to do another one, tougher one. So the end problem can be solved using a perceptron, but what about the cat problem? I don't know whether you're aware of the cat problem. The cat problem is almost as simple as the end problem. It goes like this. Instead of 2 input nodes, you have 7,396 input nodes, because you're feeding in pictures. You're feeding in little pictures, grayscale pictures, where each pixel can be between 0 and 255, 0 meaning black, 255 meaning a white pixel, and gray pixels are in between. And each picture has 7,396 pixels, and we're going to push these in here through the network. And I want you to find those set of weights such that the perceptron outputs a 1 if it sees a cat picture, and outputs a 0 if it sees not a cat picture. What are the weights going to be? Again, you can pause the video and do the calculations on a paper, and then you will soon figure out that, of course, this is a trick question, because not only is it extremely hard to find weights like this, but it's also, it's even worse, it is actually impossible. And the reason why it's impossible is, so there's no solution, that we need a more complicated model, right? The perceptron is a linear model, and our cat problem is not linearly separable. And I'll quickly explain to you for example, I'll give you an example for a linearly separable problem, which was our end problem from before, from the previous slide, where we had 2 inputs, x1 and x2, and we only had 4 possible input vectors, right? 0, 0, 0, 1, 1, 0, and 1, 1. And the green means that it should fire a 1, and the red means it should fire nothing, it should output 0. And you can see now immediately that this problem is linearly separable, right? You can find a line that separates the red axis from the green axis. And the same, of course, is true if you have many more dimensions. Then it becomes a plane, or 3-dimensional plane, or an n-dimensional hyperplane. But as long as you can use such a linear construction to separate these dots, then it's okay. Then you can use the perceptron to solve this, and you can find some set of weights that would fulfill this task. But in the cat task, it's not possible. All right, so we figured out we need to make things more complicated, and so now let's the first complication we're going to do is we're going to add more outputs. So instead of just 1 output, we're going to now have 2 outputs, or n outputs. We're going to generalize this. By the way, just real quick, this is still not going to solve our cat problem, because this is still a linear operation. But later we're going to add layers here. We're going to take this whole thing here, and we're going to stack it up, or make a sequence out of this. And if we do that, then we can actually solve the cat problem. But we'll talk about that later. First of all, we're going to add more output nodes. Now, of course, the math changes a little bit. First of all, we have to label our weights so we don't get confused. And the convention that I'm going to use here to do that is the one that's also used by TensorFlow and Udacity. Yeah, and I like those not because I'm a TensorFlow or Google fanboy, but I like those because they are intuitive. You will see later when we write the math equations here that everything nicely always goes from left, from the input, to right, to the output. Yeah, when we write these things. Just for example, like here, so the first number here, the first index is the index of the input node, and the second index is the index of the corresponding output node. And you can see here that we have now not only 3 weights, but we have 6 weights, because each node, each input, is connected with each of these summation blocks. Yeah, so the number of weights we need is always the number of input nodes times the number of output nodes. All right, so it becomes basically we're going from a weight matrix to a weight vector, and what this means for our summation here, or for our outputs, is that we have now, of course, a bunch of outputs, so we can write them as a vector, doing the same thing as we did before. We just do these multiplications here, we sum it all up, and now because we're using this convention, we have to transpose this vector. This is a column vector, right? So it's a column of numbers, and if we take the transpose, it becomes a row vector. So basically, it's the same thing. It's just these numbers should be written in a row, but because I didn't have a lot of space here, I wrote it as a column, and then I slapped the t here, which is the same thing. And again, this is necessary because later we're already using this TensorFlow convention, and otherwise the equations later wouldn't be correct. So now you can see here that we are replacing the inner product, or the dot product, between two vectors from before. Now this becomes a matrix multiplication. Yeah, where our weights are now arranged in a matrix. Yeah, and by the way, the number of input nodes is the same as the number of rows of that matrix, and the number of output nodes is the same as the number of columns in that matrix. Yeah, and then again for your input vector, which now has to be a row vector, by the way, also important. The number of columns in that input vector is the number of inputs, right? Makes sense. And also, what we can do now with this thing, because we're already using matrix multiplication, we can add more rows here to this matrix. Yeah, and those will become our samples. So if you want to push not only one sample through the network, but let's say 100 samples, you can write this. You can create a matrix like that. You can create a matrix with 100 rows and 3 columns, and then it's still just a matrix multiplication, where we go nicely from left to right, from input to output. Yeah? Again, if we didn't use this convention, if we didn't have the t here, we would have to turn things around. The indices would change, the order would change. It would all become very unintuitive. I think that's why I like this convention here. But again, there's more than one way of doing this. Okay, and okay, yeah, the activation function here stays the same. We still use this step function here. Nothing changed here. We're using 2 now, but they're both identical. All right, next slide. We're going to complicate things now. We're going to add. So by the way, this is one layer here. Everything we saw so far is one single layer, right? People sometimes make the mistake and they call this input thing here a layer, which is not true. Yeah, so there's no such thing as an input layer. The inputs here are just numbers. There's no operations going on. This here is an operation. That's why this is one single layer. All right. And also try to clear this up here by using these circles here, and the circles always mean it's a number, which tells you that you can basically use these outputs here, which are also just numbers, as inputs to another layer. Okay, so this is now a 2-layer neural network, and this is where the term deep comes from, by the way, because we're going into the depth right now, right? And if you stack up not only 2, but like 10 or 15 layers like this, then you're going deep, right? This is where the term comes from. It was coined only in the last couple of years, I think, I don't know, after 2007 or something. So it's a pretty new term, but you can see here it was already around in the 70s. Yeah, so it's kind of a new hype or hip term for an old hat. Which doesn't mean that in the 70s they were able to solve these things completely. Nowadays we are, because we're using a couple of tricks, one of which is backpropagation, but we're going to get to that later. So first of all, we have to further complicate our index scheme, and we're going deeper down into index hell. So we have another index here for each weight, which is the layer index. Right? So we're calling all these weights here, they have this one, this superscript 1, and all these weights here, which can be different. It could be a different matrix with different dimensions. They have the index 2. Also, our outputs change now. We have another index here for the first outputs, second outputs, outputs of the second layer, outputs of the first layer. Our inputs stay the same. Our activation stayed the same, summation still works the same. Everything is pretty much stays the same. The funny thing is here that now we can basically take this output here, which is this one here, and feed it back in as the input to the next layer. Right, so this output here now becomes our x vector for the next layer. That's what I wanted to show with this arrow here. So what we basically have is we just have a bunch of nested functions, and they always repeat. So the overall output, this one here, which is O as a function of the input vector, is just the output of the second layer, which is a function of the output of the first layer, which is the function of x. Yeah, and this is important, this fact that we have nested functions, that the neural network is nothing but a bunch of nested functions, is important later for when we do backpropagation, because then we have to apply the chain rule of differentiation of calculus, and the chain rule tells us that if we want to form the derivative of this term, we have to first differentiate, or build the inner differential, and then multiply by the outer differential, and so on and so forth. If we have many more nestings, this will just become a long chain of multiplications. All right, so we saw that from the cat problem. And by the way, so these multi-layered perceptrons, they would now be able to solve the cat problem. Yeah? If we make some more smaller changes, we'll get to that in a second. But now we're happy. We have a complicated enough structure that can solve many problems, many nonlinear problems. And we want to learn now, because we saw by looking at the cat problem that sometimes you have thousands of weights. We want to learn now, or we want to get to know now, how we can find these weights automatically. Yeah. And in order to do that, the first thing, the most important thing, is always to define an error function for your network. Yeah, so the error function sometimes is also referred to as the loss function, which means that yeah, how much do you lose, right? So which always should capture the difference between what the network currently outputs and what the network is supposed to output. So remember, we're doing supervised learning here. We have inputs, and each input has a label, which is basically human handcrafted, and which tells the network in a supervised fashion what it should output given some input vector. And you can use, for example, this error function here, which is sometimes referred to as the mean squared error. It's a very popular one. It captures the difference between what the network currently thinks the output is, what the network calculates for the output, minus the label, right? So minus what the human supervisor tells the network it should output. You take difference, you square those so that the terms always are larger than 0. You add them up and you take the mean, right, the average. So the question is, how does this error function help us determine how we should change these weights? Yeah? And let's just assume, for the sake of simplicity and this discussion, that our loss function is only dependent on one single weight, which is weight 20, right? This guy here. So it's a very simple function. This axis shows the weight, the value of the weight right now, and this function shows the depending the error function. And let's also just assume that the error function goes like this, which is also not true. This function will not look like this. But let's just assume that just for the sake of this discussion. And let's assume that our weight right now has this value here. How do we have to change it now in order to minimize this error? Well, if we look at the slope of this curve, if we look at the gradient, we can see that at this point here, the curve has a positive gradient. Right? So if I increase W starting from here, my error will go up. In other words, I always have to move against the gradient. Yeah? And this rule, this update rule here, this calculating the delta W's, the amounts by which I have to change my weights in order to get to this bottom here, to get to this valley, this is called gradient descent. Yeah, and it's basically saying just take the derivative of the loss function versus the weight, and go in the opposite direction. Take the minus. And this eta here, this eta parameter, is the learning rate. and you can set it to some small value like 0.0001 because you want to avoid moving in this direction too quickly, because otherwise you would end up maybe if you have bad luck, you would end up on the other side of the valley. And if you really have bad luck, then you would jump around iteratively back and forth, and you may even end up in another valley in a worse local minima. All right, so this is again this concept here is called gradient descent, and this is our update rule then. So the weight at the next time step, the next iteration, is the weight from the previous iteration plus this delta W. The problem with this, of course, now is that we don't have this term, or we will have it, but we'll have to calculate it. Eta we can set, the learning rate we can set, but this term here is basically remains to be done by us. And this is where backpropagation comes in. So backpropagation is a very convenient and very efficient algorithm to calculate these partial derivatives of the loss function versus the weights. And in order to do that, we have to rewrite the neural network that we have into a directed acyclic graph, also sometimes referred to as DAG. So we make the loss function part of this graph, and these graphs, they work like this: that you have parent nodes, and then you have operations, and then you have child nodes. And the child nodes, or the computations that the child nodes have to do, always depend on the results that are coming in from the parent nodes. So in other words, you will not be able to calculate the sum if you don't have these three incoming pieces of information here. Yeah, and then so on and so forth. So you cannot calculate the step function or the output if you don't have the sum, and you cannot calculate the error if you don't have O0 and O1. Okay, so you have this children-parent relationships within these graphs, and important is that you make the loss function part of this graph. Yeah, and if you, for example, if you program a network in TensorFlow, one of your last steps when you're almost done with the network, you start with the inputs and then you work forward. And one of the last things you do usually is you define a loss function, and the loss function then TensorFlow internally connects it to the outputs. Yeah, because you're defining it like this. You're defining that take the outputs, take my labels, and do these calculations. So the cool thing now about backpropagation is that it finds the partial derivatives of the last node versus these weights here. And it's not restricted to neural networks. So every neural network is a directed acyclic graph, but you can. This is even more general. Right? This is a more general concept. So you can, for example, you can enhance your neural network now with many more operations that are outside the scope of what we talked about when we talked about perceptrons. Yeah, so you can add more arrows here, and you can add more branching and do some looping here, as long as it's not acyclic. Acyclic means that these blocks are not dependent on these anymore. So there's no recurrent connection here that connects this back to here or something like that. Then it wouldn't work. All right, so in the next couple of slides, we will talk about backpropagation, and we will see with a simple numerical example how we can calculate the weight updates. Right? Okay, the first step you do when you do backpropagation is you pass a sample in a forward fashion through the network. Yeah, we know now how to do this. We have all the formulas we need. We know how to calculate our sums. We know how to calculate the outputs using the activation function, and we know how to calculate the loss using the outputs and our labels. Yeah? So let's start. First, what we need, of course, is we need some initial values for our weights. And what you usually do is, I use these stupid numbers here for the sake of this example here to explain this example. Normally in real life, what you should always do is you should pick small values for the weights around 0, but not 0. So you would usually do a truncated normal distribution to initialize your weights, so that the values are, I don't know, 0.1 or minus 0.2 or 0.05, something like this. Yeah, somewhere around 0. They should never be all 0, because then its learning will be really slow. So again, this is just a bunch of numbers that I made up to make the calculations easier. What else do we need? We need a sample input. We're going to take the vector 2, 3, pass it into our network, and we need a label, right? So we want our network for this sample to output 1, 1. Okay, so O0 should be 1 and O1 should be 1. We're going to use these weights here in this weight matrix. And again, the first step is going to be a forward pass. So we're going to calculate these sums first, which will give us -7 and 8. And we will activate. Remember that the activation function spits out 0 if it's smaller than 0, and it gives us 1 if it's larger than 0. And this will make our loss become 0.5. Alright, we will keep these numbers in memory, and we'll do the next step now. So the first step is complete. We have done a single forward pass. The next step, the second step, and there's 3 steps altogether. The second step is to know our derivatives. What does that mean? So we'll start with this one here. We start from the back now, and we need to calculate for each of these nodes, for each of these connections. So for each of these edges, we need to calculate the derivative of the final loss function of the final node versus the parent nodes. Okay, so this is the loss node, and the parents are this one and this one. And we can do that by looking at this equation here. So we need to calculate the partial derivative of loss versus, for example, O0. If we do that, if we plug in the values here, this term will go away because it's constant. Because when you do partial derivatives, only this guy changes. Only this guy here is the variable, meaning that this one is constant. We can it becomes 0. And here we have to do the outer derivative, which is 2 times this parenthesis. The 2 goes also away because we have 1/2 here, times the inner derivative, which is 1 because it's 1 times O0. So this is our result here, and if we plug in these values here that we already have, that we already know, which are 0 and 1, we get -1. Okay. Let's do the next one. Let's do the step function, and ouch, now we see that there's something wrong with the step function. Okay, a lot of you may have known this all along already, cringing inside saying, what is this guy doing with the step function? Yes, I notice now here that the step function, if I take the derivative over the input, it's always 0. Alright, and that's a problem. So we got to fix that. We got to replace the step function because now we're doing partial derivatives, and the step function always yields 0 as a derivative because it's like it's totally flat, right? It has a 0 slope here and has 0 slope here, so you can't really work with it in terms of gradient descent. So this is what I'm quickly going to do here on the next slide. I'm going to replace the step function, which again I've shown here, with a more modern activation function, which is used till this day, which is called the leaky ReLU function. ReLU means rectified linear unit, which is basically 2 lines attached to each other at the 0 point. Yeah, so if the input is positive, it's just the identity, right? So y equals x, and if x is negative or the input is negative, you kind of yeah, that's where the leaky term comes from. Normally it would be 0, but because you're leaking something, you have some small slope here. And this gives us a function now that's really cool, that has always some gradient, right? There's always the derivative is always some value that's not 0. It's either 1 in the positive range, or in this case 0.1 for the negative range. And that's really cool because that means that our weights, our weight updates now, they always have some value not 0, right? So if we would use a step function, we would always get a delta W of 0. And that's terrible, of course, then, because we don't learn. That the machine, the model will not be able to learn anything. Okay, so I changed the activation function. Now you can see this is the ReLU function. Before we had the step function here, and this, of course, changes these values as well for our forward pass. But it's not a problem. I already fixed that. Yeah, so our error got larger now. Our activations are a little different now. Instead of 0 and 1, we have -0.7 and 8. This value also got changed. But again, the same rules still apply. Nothing else really changed except for this operation here. And now you can see that the our derivative here for the output over the sum over this input is now some value that's not 0, which is great, which is exactly what we want. The last thing we have to do is we have to calculate the derivative of this sum here versus the weight, which is this formula here. Yeah, and if you look at this here, we have to take the derivative of this guy versus W20, which is this one. So everything else is constant, it goes away, and then only this factor here remains, which is x2. And we know the value of x2 because it's our the number that we fed in here in the forward pass. So this gives us 3. And now that we know all these things, we do the last step of backpropagation. We propagate this error here back through the network using our partial results here. Yeah, we're using the chain rule now, which is nothing but multiplying all these results here together. That's all it is. Yeah. So again, this is the term that we needed for gradient descent, and this is how you can also write it. Because these cancel each other out. This cancels out. This cancels out. This cancels out. Yeah. So let's start with this guy here. This is of course 1. dl over dl is 1, and we're going to write the 1 here. We're going to store it here. Okay. And then we're going to move back to all the parents. So we're going to do only this path here in this example to keep it simple. So the parent of 1 is this node here, and now we have to multiply this 1 here with the minus 1.7. And we do multiplication, and this gives us minus 1.7. We're going to store that value here. And once we have stored these values here, we never have to calculate it again. So basically, backpropagation allows us to calculate all these partial derivatives, all these dl over dw's in a single backward pass, visiting each node only once. So it's linear. The backpropagation is the complexity is linear with respect to the number of nodes that we have, which is very good. It's much better than polynomial or exponential or something like that. Again, we do a multiplication. We multiply in this 0.1 here, and we get minus 0.17, right? This times that. And the last thing we do is we multiply it by 3, and then we get minus 0.51. And I tried that at home with a piece of paper. You can try now changing this weight by 1, which is this number here, by the way. Yeah, the weight W0 is this position here in the matrix. If you change this value here by 1, if you make it 1 larger, you will see that your error will decrease by 0.51. The error that we had before here, which was, I believe, 26, right? We had an error of 26. It will really go down by about a half. It will be 25.5 after that, if you change the weight by 1. Yeah, so these numbers here, they make sense, and it's you can see how simple backpropagation is. A lot of times people describe it in a very complicated way, using the matrices and using a lot of these equations here. You don't really need that, and if you think about let's assume you would want to program your own TensorFlow library, you would do it exactly like this. You would just build a graph with nodes that have parents and children. Then you would do a forward pass, and for each node you would have to implement the 2 functions. The first one is to calculate its value for the forward pass, and the second one is to calculate its derivative for the backward pass. Always, of course, depending on the values of the parents and the values of the children, and the operations that these nodes do. So here you have summation, here you have ReLU, and here you have these square guys. But it doesn't matter. Each node just needs to know its own universe, its own way of forming the derivative, and its own way of doing the forward computation. And then you're done. And the trick of backpropagation is, or the fantastic thing about backpropagation is that it works. So the alternative to backpropagation is to do it the forward way, right? So you could say, I'm going to do the chain rule, but I'm going to do it the other way around. I'm going to calculate first the derivative of this sum versus the weight, and then the derivative of this guy over the sum, and so on and so forth. And when you do that, you will quickly notice that you will have to pass through the graph many times, once for each weight, right? And that's kind of crazy, because if you think about neural networks that have millions of weights, and modern networks do have millions of weights, you can quickly come to the conclusion that the backpropagation way, when you go backwards to the graph and only have to visit each node once, you're saving about, for modern neural networks, about 100 million. The factor that you're saving is about 100 million, which is the difference between training a neural network for 1 week versus training it for 200,000 years. Yeah, this is how important backpropagation was, and it's a really simple trick, but it's just super important. All right, I already said that. So now we have our delta W to 0, which is minus the learning rate times minus 0.51, which means basically that we have to increase this weight, which I already said before. You can try to increase this here, and you will see that the error will go down. The error that we calculated here before, which is not 1, which was 26 from the forward pass. All right. Sorry, I'll show this slide one more time. This will conclude our math part of this presentation. In the second part of this presentation, I will, which is a separate video, I will talk about different neural network topologies, different neural network architectures, and I will show you applications of these different topologies and architectures, real-life applications. All right, so stay tuned. Thank you for listening, and I'll see you in the next part of this deep learning tutorial.